record. Right.
Mm,
So today we have a talk from Brennan Keller, who is an assistant professor at Dartmouth College in Hanover, New Hampshire, where he joined the faculty in 2019. Previously, Brennan conducted a postdoc at UC Berkeley at the Berkeley Geochronology Center, a PhD at Princeton University, and an undergraduate degree at Cornell. Starting with a background in igneous petrology and uranium-lead TIMS geochronology, much of Brennan's work involves the long-term evolution of the Earth system, particularly including interactions between the deep Earth and the surface Earth system on geologic timescales. Brennan's research group at Dartmouth attempts to integrate field, lab, and computational perspectives to search to such Earth systems questions, particularly including both forward and Bayesian inverse modeling. So, Brendan, I'll hand it off to you.
All right. Thank you, Ian. So today I wanted to talk about Archean tectonics just because of sort of seeing the talks that have been given in VSPG in the past. I remember seeing maybe not less this year as previous years, but a number of talks about this. And it's a subject I've thought a lot about, and it's sort of where I started, something I started with in grad school and have continued working on to this day. Now some of my students work on this, so I want to give my perspective on this sort of really kind of central question of long system Precambrian and through to today Earth system evolution. So, um, if we think about what is plate tectonics, well, we've got if we think of a simple sort of cross section through the Earth, we've got probably one of the key features is we have two types of crust, one of which subducts under the other, and this causes so we have horizontal plate motions, we have magmatism at various sites. Some of these are driven by different processes. If we think about for just from first principles, are we ever just any of these sites just increasing temperature? Well, not really. Some sort of the closest we would get to this is maybe in an Archean or Hadean where we have much higher impact fluxes, bolide impacts. They melt things by just increasing temperature. But this is not really common in plate tectonics. Instead, we have a set of a range of settings where we have essentially decompression melting. You reduce the pressure, that brings you closer to the solidus, and then you melt. So mantle plumes, mid-ocean rifts, continental rifts, they're all decompression melting, which has a certain set of geochemical consequences. And then the other thing, which is the one that is to me kind of really emblematic of plate tectonics is arc magnetism. So in arcs, rather than decompressing the mantle, you add water to it. You reduce essentially it's like adding antifreeze to ice. You reduce the melting temperature by adding a flux, and then you get arc magnetism, which also has its own geochemical characteristics. Now, if we zoom out and think on the really big picture, why does this matter? I may not even have to mention this at all for this crowd, but for thinking, okay, why does it matter that we have these two types of crust? Well, these two types of crust, they're different in elevation. And this is not just a matter of thickness. So the continental crust is thicker. It's also a matter of density. And these two types of crust actually have different compositions. One, the more dense oceanic crust is somewhat similar to what we see on many other terrestrial planets. Venus has a basaltic crust, Mars has a basaltic crust. But this less dense continental crust, which is, andesitic on average, this is not really seen elsewhere in the solar system. And this change in thickness and in density results in a bimodal hypsometry for Earth, which it turns out, essentially just having a set of crust that is subaerial, that is exposed to weathering, that is exposed to rain and uh, erosion, and CO2 from the atmosphere can interact with your silicates, and you can consume CO2 in this way. This whole classic silicate weathering feedback that sort of keeps Earth's climate equable over billion-year timescales. This is to some degree really, if not completely dependent, much more efficient for having exposed continental crust, where your rainwater can directly interact with your silicate crust at the surface. And this silicate crust and the bimodal topography that results from it is fairly unique to Earth. Again, in the solar system, Mercury, Mars, the Moon, they all only have this basaltic crust. Mars has sort of like a hint of bimodality in its topography, but this is generally thought to be sort of a relic. The northern hemisphere dichotomy is probably actually a very large impact basin. And if Mars had an active hydrosphere, if it had silicate weathering like Earth, this would probably get eroded away in time. So we need something that, if we want to have a silicate weathering feedback on Earth for a long time period, we want to have exposed continental crust for many billions of years. We need something to produce and maintain this continental crust. And from just a very first order perspective, what is going into the crust from the mantle? There's a bit of a question here because the flux from the mantle to the crust is basalt everywhere. Now, if you melt the mantle by flux melting or by decompression melting, yes, there's variations, but the first melt you get is always a basalt. So what's going on, uh, in this continental box to give us felsic crust? So differentiation is a big question. One of, I'd say, probably the leading hypotheses has to do with the fact that when you're doing flux melting, you're adding water to the mantle, you're also decreasing magma viscosity, and this is useful for differentiation because then your fractional crystallization is much more efficient. So this production of this felsic crust may in fact be very much linked to having modern style, at least platonics that takes water into the mantle and produces flux melting. Um, so if we want to have equable climate over all of Earth history, then maybe we also need most all of Earth history. Maybe we also need this subduction. And so there's, for that and for just wanting to understand it, there's been a lot of proposed suggestions for the initiation of plate tectonics. This is a figure from sort of when I started thinking about this more than a decade ago. I took the liberty of just adding, here, what are some more suggestions in the last 5 years or so? And while there's maybe sort of more of a movement to older times, there's still plenty of variation in the proposed initiation of plate tectonics in the current literature. And perhaps relatedly, there's many different proposals for the accumulation of felsic continental crust. How much do you have early? Do you have something like this Roses and Cornaga 2018, essentially modern volumes by the Hadean, or are you growing your continental crust more slowly? And this, in general, the earlier one, the earlier accumulation of continental crust is often linked not explicitly but implicitly with an earlier expectation for the onset of plate tectonics. So some of the fundamental questions we want to think about here: how has the composition of preserved continental crust changed over time? How long has plate tectonics been operating on Earth? And how is continental crust produced? We're going to talk mostly about the first two. We're not really going to get into the third one too much, but um, just to set the stage here. So the way I came into thinking about this, starting in grad school, was thinking about, okay, can we use in many Earth system processes, we can use temporal trends to tell us something about process. So like in paleoclimatology, you can see if you just look at a measurement from really just one place on Earth, you can see clear interpretable trends, in this case, glaciation and deglaciation repeating, and you get information about process from a temporal record. And we wanted to do something like this for continental whole rock geochemistry. But at first order, you don't really see a similar trend in, say, potassium, a whole rock of basalts over time, even though to some degree, potassium and basalt should vary with the melting temperature and melting extent of the mantle that produced those basalts. Should be, in a sense, a crude mantle thermometer. But we're not really seeing variations if you just look at the raw data. So this led back in 2012, Blair and I, to start thinking about, okay, what can we do if we have the continental whole rock geochemistry that we have? So thinking about anything that's preserved in the continental crust. We've got a sampling of, certainly not even, but of most continents, of most tectonic settings. Can we essentially replicate the averaging that the atmosphere does for us in that paleoclimate example? The fact that we have this huge dispersion here in contrast to a clear interpretable signal in an atmospheric record arguably has a lot to do with the relative mixing timescales of these two reservoirs, right? The lithosphere is not well mixed on geological timescales. The atmosphere very much is. So can we replicate that? And so what we did back in 2012 was we take our data set, we do some weighted random sampling to try to reduce the sampling bias and the unevenness of the initial data set. Add Gaussian uncertainty to represent essentially the noise, the uncertainty in the data set, and then bin and average to increase your signal to noise ratio. Repeat this many times to get an uncertainty of the resulting average, and then plot that. So originally this weight was essentially just trying to maximize the evenness of the data set. It was inversely proportional to sample density in space and time. And that works pretty well. There's a few edge cases where this may introduce problems. Say if you imagine you have a rock type that is oversampled, but is very well spatially distributed. So think about something that like weird peralkaline volcanics, peralkaline intraplate rocks that are spatially relatively well distributed, but they're oversampled by geologists because we think they're cool. This sort of approach won't fix that, but so we're considering other approaches at this point now, including if we can bring in additional information from geologic maps to obtain better weights. But really, as far as the entire result you get, the weighting is a smaller proportion than essentially just properly propagating your uncertainty and increasing your signal to noise by averaging. So here's an example of what that would look like if we take that same raw data, we resample it, essentially some of these lines that were overly quantized but had very large time uncertainties spread out. And then the averaging is what's really doing the increase in the signal to noise ratio. And now we can see a trend. Essentially, this potassium is higher now than in the past because of a decrease in mantle melting extent. So, well, I'm cutting ahead a little bit, but so um, if we're going to think about using this approach to interrogate the composition of the continental crust and what that tells us over time and what that tells us about plate tectonics, we wanted to start with basalts because again, this primary magma flux from the mantle to the crust is basalt. It's what you're starting with. It's arguably the simplest thing to look at the geochemistry of if we want to say something meaningful about tectonic setting. So starting with that, a number of trends were immediately obvious to us, particularly a set that decline over time, which are basically in elements that would prefer to stay in the mantle than going into the melt, and a set that increase in time in basalts, essentially the ones that would prefer to go into the melt. If it's a trace element, we would say incompatible. And so this was not at all a surprise to us. This is basically just consistent with a decreasing mantle melt fraction throughout Earth history. So if we think about an element that would prefer to stay in the mantle, let's say magnesium or chromium, these are higher in the Archean because you have a higher degree mantle melting, in any given single, in the production of any single basalt or komatiite or whatever in the Archean, you're generally melting the mantle to a higher degree, so you're forcing your melt to be closer to the bulk composition. If you go to the extreme of you melted the mantle 100%, then your magnesium and chromium would be as high as they are in the mantle itself. And then as you decline from that, your concentration in the basalt goes down. And then your incompatible ones are just, or relatively incompatible ones are just the opposite. They're most concentrated when your melt fraction is lowest today, and they decline essentially due to dilution as you go back in time. So, okay, that's fair enough. We could use that to estimate essentially what percent mantle melt did produce those records if we take all of the major elements and compare that to models of melting the mantle with P melts. There are a number of potential biases that could shift this record up or down, but overall, this sort of decline from 30 to 40% in the Archean to 10% today is consistent with what we were expecting from other methods. And we can also use this to estimate a temperature, change in mantle temperature over time. And here, the absolute value of this temperature, there are a number of biases on this, essentially to do with the fact that we're not looking at purely primitive basalts. We're looking at any basalt that is preserved in the continental crust, which may have some amount of differentiation in there. So a number of biases could push this up or down, but unless that relative degree of differentiation is changing through time, this trend through time should be telling us something meaningful. And again, just before we get too far into this, I want to reinforce here. So this is looking at basalts that are preserved in the continental crust. So we're not looking at morbs here primarily. There may be incidentally some in here if there's an ophiolite that abducted a morb, but primarily we're looking at continental arc basalts, island arc basalts that then got accreted to the continental crust, continental rift basalts, and continental intraplate basalts. So anything that is arc, rift, or plume setting, but is producing basalt that is preserved in the continental crust. Okay, so far so good. This is kind of what we expect from declining radiogenic heat production over time, loss of heat from the interior of the Earth due to secular cooling. This is not a surprising trend, but there's some other things that we saw pretty early on that were more surprising to us. So a number of trace element ratios, still in these preserved continental basalts, had relatively sudden changes across the Archean Proterozoic boundary. And this was interesting to us because if you think about trying to model this as okay, well, we have our mantle melting extent that we estimated from the major elements. We could, choose some set of partition coefficients for each trace element that we're looking at, and choose some sort of constant mantle composition. Can we fit these? Turns out no. So if you can try to make it fit for the Archean, and then it doesn't fit for the Proterozoic and present, or you can try to make it fit for the Proterozoic and present, but then it won't fit for the Archean. So there's some sort of mismatch here between, at least if we're thinking about a relatively simple model with constant partitioning between the mantle and your melt, and with um, the mantle melting extent that we estimate from the major elements. We can't quite make this all link up. So something else has to be changing. Some of the first things we thought about, like, okay, could this be the initiation of subduction? You're changing your trace element ratios because you're changing the actual process by which you're melting, or changing the proportion of style of subduction, or sort of um, more ambiguously changing the systematics of mantle melting, which we'll get back to that later, it turns out. But so thinking about this first one, subduction initiation, because many of the compilation of studies that have proposed an initiation for plate tectonics, many of them have suggested something around the Archean Proterozoic boundary. If that were the case, if we essentially had stagnant lid in the Archean, and then we shifted to subduction subsequently, we should see a big change in the amount of slab fluid input, because essentially we'd be turning on this arc flux at that time or over that interval. So we might expect, if we think about trace element ratios that are more fluid mobile versus not fluid mobile, we could probably come up with a trace element test for this just in the basalts, following the modern arc signature. And we might expect it to look something like this, where this sigmoid would be going up wherever we think plate tectonics started. So for all the times in that trend, maybe it would be here. There were a lot of studies suggesting 3, so maybe that should be here. But we should see some sort of sigmoid function between our like rift type and some mixture between rift and arc subsequently. So well, we can just try that. Here's one of probably the better, more favored ratios for looking at slab fluid input: niobium thorium. So niobium is one of the most fluid immobile elements out there. It's a 5+ ion. It's tiny. It does not want to be in a fluid at all. Thorium more so, but still not so fluid mobile that we worry too much about this getting reset by later alteration. And just to give context, modern arc basalts often average a bit over 4, whereas modern rift and plume interplate basalts are often around 10. So what do we see on here when we look at the average of everything that's preserved in the continental crust? We're consistently more on this arc side, given some variability, but certainly not the sort of sigmoid we were looking at previously. One other way we can think, because again, these are trace elements. There's many nice things about trace elements, but they are potentially susceptible to alteration and resetting in some cases. Can we do this with major elements instead? So the next thing that we looked at there is tholeiitic versus calc-alkaline differentiation, which is really one of the classic differences in terms of petrology between magmas produced at in a decompression setting, a plume or rift, and magmas produced in an arc setting. Arc basalts are typically calc-alkaline, which, in sort of really simple terms, essentially means that as you differentiate from a primitive basalt with perhaps 8 to 8% magnesium down to something a bit more evolved, your iron is going down as you differentiate if you're in a calc-alkaline differentiation trend. And broadly speaking, it's going up if you're in a tholeiitic differentiation trend. And particularly, my favorite way to think about this is as this tholeiitic index, which was introduced by Zimmer et al. 2010, and which they showed corresponds very nicely with magma water content. So, the more water you are putting into the mantle, the more concentrated water is in your melt. If this is the flux melt, you should be more tholeiitic. Essentially, 1 would be a tholeiitic index of 1, since this is just how much iron you have in magmas with 8 to 8% magnesium versus 4. 1 would be no change in iron concentration as you differentiate. A tholeiitic index greater than that is your iron is going up as you differentiate, and lower than that is it's going down as you differentiate. So that's relatively simple. Before we look at our data in that form, though, let's just look at it as the differentiation trend itself. Just plot magnesium versus iron. And we can bin this sort of crudely by time, so 0 to 1, 1 to 2, 2 to 3, and 3 to 4 billion years ago. And again, if our ortholytic versus calcalcaline is, do you go net up or down in differentiation between sort of about 8 and about 4 weight percent magnesium. But we don't actually see too much change in the shape of this trend. There's maybe some overall shifts up or down, which probably have to do with your initial primitive melt, your mantle melting extent and your melting pressure. But we don't really see much of a change in the onset of magnetite fracture, or more broadly, iron titanium oxide, magnetite and ilmenite fractionation, which is generally thought to be probably the mechanism that links your water content both directly and perhaps more indirectly through redox to your iron concentration during differentiation. So this is, if this is to be taken taken for granted, this is essentially saying that we are not really changing our tholeidic versus calcalcaline character of differentiation, from 3 to 4 GA all the way to the present. We could look at this other ways as well. So hey, here's instead of versus magnesium versus silica, and then just looking at the iron to magnesium ratio. And again, we're not really seeing much of a change in the angle or slope of this. We're just seeing an overall shifting up or down due to the degree of mantle melting, not so much a change in our tholeidic versus calcalcaline character of differentiation. So coming back then to the sort of same framework we used before, if we use Zimmer's tholeidic index, here modern non-arc basalts are averaged about 1.1 or so. Modern arc basalts maybe 0.85. What do we get over time? Well, consistently arc-like all the way back to the oldest hull rocks we have in our data set, which would be Ishua at about 3.85 billion years ago. Okay, so this is to me suggesting pretty strongly a constancy in the ratio of flux to decompression melting. There's not really despite many other interesting things that do change, there's not really a change across the Archean Proterozoic boundary or within the Archean in the proportion of magmas that seem to be differentiating in the way we expect for a hydrous flux melt versus a dry decompression melt. And it suggesting that we have perhaps plate tectonics in a relatively modern style going on for this entire time period. However, there are some other things that do change across this boundary. So we mentioned this problem earlier. Some of our basaltic trace elements vary more rapidly than we could explain by a single constant set of mantle compositions and partition coefficients. Uh, so coming back to this, if we rule out these ones on the basis of our slab fluid input and calcalcaline versus tholeidic differentiation, focus instead on this last one. Well, we know that the extent of average mantle melting that produces any particular basalt has on average been changing pretty dramatically over the last 4 billion years. We can model what this should do to the mineral proportions in the residual mantle as a function of time. So say if we are in the Archean, we have, our particular basalt or whatever that we're looking at has been produced by melting a given parcel of mantle to about 35%. Well, the mantle that produced that basalt should no longer really have any garnet or clinopyroxene in it. So those become exhausted around 30% melt. So if your given packet of melt experiences more than that, they're gone. That's going to influence partition coefficients. And then your other the minerals in your surviving residual assemblage are also changing in proportion. So we actually probably shouldn't expect our partition coefficients to be constant as a function of degree of mantle melting, which is in turn changing over time. So if we incorporate this in the model, we get these big changes in let's say for our lanthanum ytterbium ratio, both the numerator and the denominator. And if we combine that again with our estimated partition coefficients versus percent mantle melt with our estimated percent mantle melt through time, now we actually are fitting these sorts of trends pretty well. And this applies to basically all of the ratios I was showing you sort of more sudden changes in before. So I would argue really that, although there are a number of changes that are seemingly sudden here, at least in the basalts, these seem to be a natural consequence of secular mantle cooling. Okay, so we mentioned before that amount of felsic continental core and also composition of continental crust has also been linked historically and conceptually to the onset of plate tectonics. So let's think for a minute now about how felsic was Archean crust. There's been debate on this front too. A number of papers suggesting that perhaps the average continental crustal composition in the Archean was more mafic than what we would expect from modern style plate tectonics, and others suggesting that it was relatively similar to modern crust. So when I'm thinking about this sort of problem, the very first question is, just like in that last example, well, what's going to change as a result of changing mantle melt percent, changing mantle temperature and mantle melt fraction as a result? So if we think about just again, like a P melt model of melting the mantle, well, some of the element like magnesium, which would prefer to stay in the mantle until you've melted it all the way, that shows a strong variation with percent melt. Certainly, our trace elements are going to be varying a lot with percent melt if they're compatible or incompatible. But our silica content, the thing that we're actually talking about here, is relatively flat with percent melt of a mantle peridotite. So we might actually not expect this to be changing too much as a function of secular cooling, but we might expect essentially everything else to. So, for example, if we think about potassium versus silica, what does our trend look like? Well, sort of similar to our iron and magnesium examples we were looking at before. While there's some sort of vertical offsets driven by changes in the extent of mantle melting, which is essentially changing your starting composition here. So if we keep this in mind, the relationships between essentially more or less any element or ratio and silica is not necessarily going to be the same in the Archean. That puts a new perspective on some of the sort of indirect proxies, trace element or other proxies that have often been used to estimate crustal silica in those papers I was just showing. So, for example, the Duim et al. 2015 paper used this interesting estimate of rubidium-strontium ratio over time to suggest a change in from more mafic to more felsic compositions, and then use this rubidium strontium ratio of a it's actually not of the observed crust but of it's a model ratio based on strontium isotopes, but then use that ratio to estimate silica based on the present day relationship between silica and rubidium strontium ratio. Well, I like this is a nice approach in principle. It's always nice when you can get more information out of uh, you know indirect data that may not be subject to some of the same preservation biases as just looking directly at, oh, well, how felsic are preserved Archean crust. But this is going to be a problem when the proxy you're looking at also probably changes as a function of silica. So in this case, rubidium strontium ratio versus silica changes quite drastically from the Archean to the present. So what we are thinking of as like in a modern crust representing 60% silica might represent more like 70% silica in the Archean. So if we put that together with, put that trend together with what we expect for constant silica crust, just make a model crust that has all the same proportions of basalt, andesite, dacite, rhyolite in terms of igneous crust as present day crust, we actually get a trend that looks almost exactly like what we might all observe with just a different vertical scaling, given that one is looking at actual crust and the other is looking at a model sort of primitive crust. Um, so I think this is suggesting well, we may actually not need any change in crustal silica. A lot of these same issues apply to other proxies, which have been used to also suggest a change in crustal silica across the Archean Proterozoic boundary, or sometime within the Archean. So I don't think there's actually in the end much uh, compelling evidence for a major change in crustal silica through time, continental crustal silica. But we have a lot of interesting things resulting from secular mantle cooling. What else can we think about though? What did change across this boundary? So we know things have cooled. So if we look at felsic rocks, there's a very famous signature to do with Archean granitoids being more sodic, what is often called the TTG signature for the trondhjemite tonalite granodiorite signature. Archean rocks fall in a narrower, or felsic rocks now, 60 to 74% silica, fall in a narrower compositional range on a sodium, potassium, calcium ternary, more towards the sodium end. And this is associated with a lot of trace element variations in this felsic crust. So if we go, way back to the first time we were thinking about this in 2012, lanthanum ytterbium is generally higher in Archean granitoids. This is oftentimes considered part of the TTG signature. And also you have less of a europium anomaly. You have sometimes no europium anomaly at all, EU over EU star of about 1 in Archean granitoids, whereas modern granitoids, which have since they've fractionated a lot of feldspar and getting to be a granitoid, often have substantial negative europium anomalies on average. Okay, so we can look at this in the same way we were looking at our iron and magnesium before as well. With, let's think about an actual differentiation trend rather than just you know, bin versus time only. And we see a number of interesting things in here. So if we think about a number of elements that may have something to do with feldspar, we do see major changes in differentiation from the Archean to the present. So part of this may be driven by the fact that our starting composition is again different due to the fact that our mantle melting extent is different. So our starting composition that we are, the basalt that we are trying to differentiate to granite from has been changing over time. But there's also a number of changes that don't seem to be explainable by just that. So say if you think about sodium, in all cases, as you start differentiating a relatively low silica magma to something higher silica, on average, your sodium goes up until you start saturating enough feldspar, essentially albite, that captures that sodium, fractionates it out, prevents it from increasing further in the residual melt. This does not happen in the Archean. You blow right through that threshold and go to higher actual absolute sodium concentrations in Archean granitoids than in modern granitoids on average. Our europium anomaly, again, Proterozoic and Phanerozoic differentiation trends are quite similar here. Europium anomaly declines consistently as you fractionate, presumably due to primarily feldspar, which will accept europium 2 plus, but not europium 3 plus into its crystal structure. But in the Archean, this plateaus. So perhaps at a similar time to this sodium, uh, you not falling over and declining, we get a plateau in the europium anomaly. So something is we're not whatever we're doing, whatever assemblage we are either fractionating or differentiating by partial melting. In an equilibrium case, it doesn't really matter which we're thinking about. Whichever that is, that assemblage is not taking europium. It's not taking as much sodium as it did before. It's also there's also a delay, which may be pointing to this actually involving feldspar. There's also a delay in when your aluminum starts declining, feldspar being a luminous phase, and similar strontium, another trace element that likes to partition into feldspars, particularly uh, uh, plagioclase feldspars. This decline it starts much later. So some of this may be due to the change in starting extent. Some of it may be due to more complicated petrologic factors that we need more modeling to explain. But there is something different about differentiation between Archean crust and modern crust. So here's a set of elements that I often think of as having perhaps something to do with feldspar. Here's another set of trace elements that rare earths that may tell us something about more mafic phases, garnet or amphibole that we may be fractionating. There's this big change in lanthanum ytterbium during differentiation between the Archean and later rocks. Proterozoic and Phanerozoic, relatively similar differentiation trends with respect to average lanthanum ytterbium. But again, in the Archean, well, you start lower, but then you end up higher. So there's a much greater increase in lanthanum ytterbium ratio of your magma as you differentiate in the Archean than there is today. And this is also something that this results in the part of the classic TTG signature of high lanthanum ytterbium, but it's arguably even more impressive if you think you're coming from lower. Well, the first thing that I think, from a chemical petrological standpoint, to differentiate what is driving this, is this garnet, is this amphibole, is this something else, is to look at light versus middle rare earths as opposed to middle versus heavy rare earths. So many minerals can produce a high lanthanum ytterbium ratio by essentially just enriching the right light relative to middle and heavy rare earths. Amphibole could do that. But that's not where the majority of our signal is coming from. It's actually coming from the heavy rare earths. The majority of this lanthanum ytterbium is really it's from the latter half of that, the middle to heavies, which is probably more diagnostic of garnet. And similarly, in absolute terms, there's actually a depletion of some of your heavy rare earths like lutetium, which suggests that something is in fact removing this. This is net compatible in your fractionating assemblage as you go from, say, 57 to 65% silica. So altogether, this is, I think, qualitatively suggesting perhaps a role for decreased plagioclase fractionation and increased garnet fractionation in the Archean relative to later times. We can also look at this if we want, sort of more time resolution. We can just look at what is the ratio for on average all the felsic. Oops, sorry for the change. Average all the felsic rocks, like our 64 to 72% silica, divided by this concentration of the same element or ratio in your basaltic starting composition, and plot that over time, which is what we have here. And we see some pretty sudden changes roughly across the Archean Proterozoic boundary here, which are not, at least not directly explained by secular cooling. They may be indirectly explained if the change in starting mantle composition dramatically changes uh, how you differentiate in a sort of nonlinear way. Uh, but it's possible there are also changes in, say, average pressure of differentiation, or something else about the process by which you are differentiating from starting with a basaltic mantle-derived melt to eventually getting to a granite that is emplaced in the continental crust. So to try to figure this out more, this has actually become one of the chapters of my PhD student at Dartmouth, Junita Yao, who's attempting to do a parallel Bayesian inversion for differentiation conditions, given the differentiation trends we see in the Archean and later. This turns out to be quite hard in a number of ways, partly computationally. If we want to do a Bayesian inversion for this, we need tens or hundreds of thousands of steps of a Markov chain. We need to make a proposal, run a forward model like melts or perplex that will simulate what the melt composition should be at each step. That can take on the order of minutes. And if you need to do that tens of thousands of times, you're in trouble. So we have to parallelize this inversion. We have to run this on a cluster. We have to use MPI to do a sort of like a replica exchange approach. And then like actually fully capturing all of the major and trace element variations in a way that also stays faithful to the ratios requires us to care not only about fitting a differentiation trend to the mean differentiation trend. We also need to worry about the covariance at each bin that we are trying, in this case silica, but each bin of our independent variable, we need to worry about the covariant structure of that. So figuring out how to do that well has taken a long time, and still in progress, and I'll let Janita discuss the results at another time. But I think this is at least a promising approach to try to see what is different about differentiation in the Archean, because I do think there is something different here. Okay. Uh, so if we come back to our sort of setup here, initiations of plate tectonics. So certainly I would be in the greater than 3.85, greater than the oldest preserved rocks we have in the continental crust camp here. How do we think about all this variation in proposed initiation times? So I think when I look at this sort of figure today, probably the first thing I think about is, well, how much of this is actually a date of onset, and how much is implicitly a one-sided constraint given preservation bias? So I've, you know, thinking about this, if you think about like where do these youngest constraints come from versus these oldest constraints, and at least this is not something that's easy to quantify, but qualitatively at least it seems pretty clear to me that the youngest constraints are the ones that are most subject, coming from things that are the most subject to preservation bias. So say these ones in the Proterozoic, you're looking at things like preservation of HPLT, metamorphic assemblages, paired metamorphic belts, like preservation of blue schists and jadestites and things like that. Which those, for if you study those, getting like a blue schist from the mantle to the surface without retrograding it is hard already. Let alone, if you leave a blue schist in a standard continental geotherm at depth, let's say green schist facies for a billion years, you're going to have a green schist. These are signatures that are easy to reset, and even though they're very interesting signatures, and it's very interesting that they do happen at this time, I think they're really a one-sided constraint on when plate tectonics starts. So many, and I think when you go back farther, you start seeing constraints based on, say, preservation of ophiolites or various mapping and geochemical based proxies. And then some of the oldest ones, we're not even looking at, the oldest we could possibly suggest as an initiation for plate tectonics based on whole rocks is roughly 3.85 to 4 billion years, because that's the oldest preserved whole rocks we have. So to go beyond that, you're only going to get an answer that's in here if you have the ability to look at something that is still preserved from there. So say, preserved Hadean zircons or more indirect isotope proxies. So my view on this is, okay, yes, there's clearly no clear consensus in the literature yet. But my take on that is a lot of these may be pointing down rather than just to the side here. All right. So coming back to our fundamental questions, how has composition of preserved continental crust changed over time? I would argue it's changed in a lot of very interesting ways that almost entirely seem to just come back to higher degree mantle melting in the past. So this has the direct consequence for the basalt. It's got slightly more confusing consequences for our basaltic trace elements and for the major elements, because you have to think about the composition of the residual mantle assemblage, but that seems to work out. And it's possible that we will essentially get something similar for the differentiation to felsic crust, even though that may have very interesting consequences. If there is a big change in pressure of differentiation from the Archean to the Proterozoic, maybe this does have a big influence on, say, things we care about for life, like redox of the resulting magma, and mantle melting declining through time. This uh, changes the abundance of basically every element but silica in the resulting melt. So that includes things like phosphorus, primary limiting nutrients for life on Earth. So on one sense, this is a very simple answer, but the variations, even though we're probably having a relatively similar silica crust through time, there's a lot of variations elements that we care about from a geobiological standpoint. For how long has plate tectonics been operating on Earth? I would certainly argue throughout the entire preserved rock record. Can't really say anything before that from this approach. And I think it's important to keep in mind preservation bias when thinking about various estimates for the onset of plate tectonics. For continental crust, I think given time, I'll maybe leave it there. I would argue this probably involves fractional crystallization in arc settings because you need to delaminate a residue. Many details remain uncertain. Hopefully, we will learn more from more things like this Bayesian inversion for differentiation conditions. All right, and I think I'll stop there.
Great. Thanks so much. That was really nice talk. Um, we'll sort of open up the floor to questions here. There's a couple ways you can do that. You can either send through the chat and I can read this out, or with the react button, you can also raise your hand. Um, and yeah, feel free to get started there. Greg, you can go ahead.
Oh, that was magnificent. Thank you. And I'm still trying to absorb it all. Um, I'm wondering, you seem to be mainly concerned with introduction of water into the crust. Um, what about the introduction of my special sauce, weathering products,
Ah,
aluminosilicate minerals that are already on the way to felsic anyway? Um,
yeah.
couldn't that play an important role?
Yeah, I'm certainly a big fan of subduction erosion and sediment subduction. I think about these. I think these processes have a big impact on the resulting melts. Uh, if we think about, let's see, what about some of our ratios? Um, so there is a big decline in aluminum of the starting primary basalts through
Right.
time. That doesn't necessarily mean, though, that we don't have as much sediment subduction going on, though, here, because this is, again, going to be driven primarily by mantle melting extent. There's only so much aluminum in the mantle. As you increase your melting extent, that's going to go down. And I think that's going to be the biggest signal. Where's our if we look at art like this, this decline in aluminum as you melt the mantle more and more. I think
Mhm.
that's primarily driving that starting composition. But I like in terms of what you get, I would not at all diminish the role of either assimilation or sediment subduction erosion, bringing existing crust into your melt. I would just probably argue that if we think about on the big scale are like are we doing this in an arc setting? I would say consistently yes. So just suggest that perhaps that term has been relatively constant through time, that we have been doing this consistently all the way back to the early Archean.
Well, I was not thinking so much about the difference between tholeiitic and calc-alkaline as the difference between basalt and granite.
Oh,
And
oh, in terms of differentiation.
yes, in terms of TTG, Dick
Uh,
Holland, as you know, did a lot of work on Archean paleosols, and I was working with him on it, and we were always kind of blown away at how they tended to be bauxitic.
ah,
A lot of
yeah.
aluminum. Yeah. Um,
Fair.
have you thought about that as a possibility?
That we should keep that in mind in terms of the, in terms of the inversion as, what is the assimilation term doing? Um, I definitely always tend to think of this from a mass balance, a big scale mass balance perspective of, well, yes, you can certainly assimilate and incorporate existing crust to make your crust more felsic. But
Uh-huh.
at some point you have to start with, where's I was going to bring back our this one. And aluminum we're certainly not fitting perfectly in these inversions, so
Right.
maybe there's a role for that there. But in terms of like the big scale, how do you make continental crust? Well, at some point we have to start from scratch to get the volume we have.
Right.
But that's not to diminish the importance of assimilation and incorporation of existing sediments as a process that does happen during differentiation.
Well, it seems to me the rare earths must be really important because the heavy rare earths are strongly enriched by soil formation.
Uh,
And your data went by pretty quick for me, but
yep.
does that support a role for incorporation of weathering products into even the calc-alkalines?
Yeah, I mean, the question would be how much is it changing over time? And I don't know. I should look at the papers you're referencing, but how much is that material that you'd be incorporated enriched in light to middle versus light to or middle to heavy rare earths? But it would be interesting to think about for sure.
Fascinating. Thank you so much.
So we have a question here in the chat from Francis saying, what about the significant degree of silicification of Archean crust, especially Paleoarchean, at the rock-water boundary? How would that influence the silica content through time?
Ah, well, it might bias preserved crust higher than extant crust. But actually, we haven't made a plot of that here. Uh, yeah, at the crustal scale, it depends where the silk is coming from. If the silk is coming from elsewhere in rocks of similar age, and you're just sort of transferring it from one phase to another, then it will do different things to the averages if it's coming from younger rocks. So I guess it depends.
I'll ask a quick
Can I
question.
come back?
Oh,
Thanks a lot, Brennan. I want to come back to that question because the silica is coming from it's coming from dissolved silica in the seawater, as
Mm.
well as the devitrification processes of the volcanic rocks, the volcanic sediments.
Oh,
So
so
it's
so
basically
um,
in situ formation.
so relatively early, relatively around
Yeah.
the time of preservation. Yeah, that could. So then it's a question of how much has that changed over time. We do see a lot more silicification in Archean rocks, as far as I understand. So that might be pushing the Archean crust more higher in silica than it would be otherwise. Yeah, that's fair.
Well, just something to keep in mind.
Yeah.
Thanks.
all right. We've got another question in the chat here from Jeffrey. Do you make a distinction between a subduction signature and plate tectonics, with the idea that the former could be produced by isolated port subduction zones and not global system of interconnected plates?
Yeah. Yeah, that's fair. So when we think about just the either the trace element or the major element signatures of our flux versus decompression melting, either the say the niobium thorium or our tholeiitic calcalkaline. For either of these, um in order to get down here, it doesn't really matter what your mechanism for getting water into the mantle is. Any way you do it is fine, and it doesn't have to be constant through time. What does have to be constant through time is sort of the ratio. So when I think about this, just the value being down here doesn't require it to be continuous modern style plate tectonics. It could be episodic, isolated, other things like that. However, one thing that I think does suggest that is at the bigger scale, this in the relative constancy of this entire trend, this fraction being roughly constant from the Archean to today. This seems unlikely to happen if there were large variations in how much water you have coming in over time. If we go from episodic in the Archean to more consistent today, then those episodes would essentially, while they're happening, take in more water than your modern subduction is to sort of make up for the times where they're not happening, in which you should be getting purely a fullytic differentiation. So for it to all average out to a roughly constant trend on the big time scale, that maybe suggests a more constant and perhaps regulated, like something with a negative stabilizing feedback, like we might expect to happen for plate tectonics. So yes and no, I guess, would be the answer. Just in terms of, could we get a single point down here without modern style subduction? Absolutely. Would I expect this entire trend to be as constant if we had major changes in the way tectonics works? I think probably not, but this could be a question for modeling. Maybe this would come out if you model stagnant lead. Maybe that becomes a question for interesting geodynamic modeling. But sort of, I wouldn't expect to see this level of constancy if there were major changes in style. But I can't absolutely rule it out at all.
We've got another one in the chat here from Ilya. He's saying, if solely due to the higher degree of mantle melting in the Archean peridotite, garnet would have been exhausted, leaving no garnet signatures to hang to YB and the heavy rare earth elements. So lanthanum ytterbium would be lower, not higher in Archean basalts.
So that would be true if you were thinking we were melting the entire mantle. So this is when we're talking about our mantle melting extent here. We're not talking about, in the Archean, we melted the entire mantle to 30%. This is of a single parcel of mantle that is undergoing melt. So if you're in a plume, this would be only the part that is upwelling and is undergoing melt. If you're in the mantle wedge, this is only the portion of the mantle that is being actively fluxed. So we're not talking about exhausting the entire mantle here. And then if we're thinking about a plate tectonic setting, we also need to keep in mind all the processes that return things that we extract from the mantle back to the mantle. So if we're thinking about if we think about producing continental crust by fractional crystallization for mass balance, we probably have to return a lot of that cumulate, which we produce to turn a basalt into a granitoid. That cumulate is going to be very rich in garnet and pyroxene. For mass balance, we probably have to delaminate that back into the mantle. So we're going to be remixing that back into the mantle. So the question of like is the mantle more depleted now than in the Archean really is entirely a question of have we increased the volume of continental crust dramatically over this time, which I would argue we probably have not, sort of favoring the more constant continental crust models. Because I think plate tectonics generally is it does a lot of recycling. Generally is likely to do that. If we were talking about melting the entire mantle to these degrees, then yes, that'd be absolutely right. But that's an important caveat. That's not what we're considering here.
Or I'll ask a question myself. I'm kind of curious if you can think of some signature we could look for that would kind of suggest that we did not yet have plate tectonics from a sample, because I guess there's a lot suggesting we do, or it must have started by X amount, but to say it cannot have started by.
Could not have. That's a hard one. I'm not sure that there is anything you can do for a single sample. I think if we said on the global average, if we were getting purely fullytic preserved crust, end member, no slab input, end member tholeiitic, then we could say, oh, there was no, if we were on the average, if we were say we were up here and not down there, then I might interpret that as yeah, we didn't have plate tectonics. But I'm not sure there's really anything you can do from a single magma because again, like the lithosphere is just so heterogeneous. It's this whole problem we're thinking about here. We have so much variety from place to place. The lithosphere is not well mixed. We're really limited in a lot of ways in what we can say from one sample, especially about negatives. If you have one sample and it perfectly records some particular process, we could find one sample that, definitively proves that we had, at least in that place, shock melting in the Archean or something. But it's hard to have a single sample that definitively proves we didn't have something. Maybe there's something I'm not thinking about, but I can't think of one. It's a great question, though.
So, Paul, you can go ahead.
The evidence of the absence of plate tectonics would be a continuous snowball Earth.
Ah, sounds good to me. Well, could we have had that in the Hadean? Is that on the table?
We've got another one in the chat here from Marcia. Do you have a hypothesis about why garnet was more important than plagioclase in Archean magmatic differentiation?
The first order thing that comes to mind for me is pressure. So if you're differentiating at greater pressure in the Archean on average, then generally that's going to, a lot of plagioclase stability decreases for given temperature as you go to higher pressure. Garnet, it increases at a given pressure as you go to, or increases at a given temperature as you go to higher pressure. So I often think of this, too many slides here, as the not having as much plat fractionation and having more garnet fractionation may be suggesting greater pressure of differentiation or fractionation, however you're doing that. But this isn't completely satisfying to me. The first thing that comes to mind, but I'm always a little unsatisfied because if we think about where differentiation happens in a modern in modern continental crust, where are we taking a basalt and turning it into a granite? I think probably one of the best places to look is at the base of arc crust, where you probably have pooling at the moho, you probably have fractional crystallization, and then delamination of residual cumulates. But that's happening quite deep today. So definitely deep enough to have garnet saturation. So why it's even seemingly even higher pressure or more universally at higher pressure in the Archean, even if I think that's the first thing that comes to mind. That's what something I've been expecting we'll find from Janita's inversions, but that's the first thing that comes to mind. But I don't love it in some ways because of how deep we're already doing this today, I think.
We've got another one here from Hua asking, given the growing evidence that the lower crust is not predominantly mafic, it could substantially influence our understanding of the crust's overall composition. Have you thought about this?
Yeah. Yeah. So I think this is probably true. That the lower crust is not as mafic as we used to think. I've actually one of my master's students also worked on this. Galen piece doing a seismic estimate for composition of deep crust, and we have a number of literature estimates on here, and then our Bayesian inversions based on perplex and Bayesian inversion based on perplex modeling of preserved crust. We really don't have that much vertical compositional stratification in those results, which, if true, I think does sort of change the way we think about the structure of continental crust. But to me, this is not like a huge surprise in as much as, well, if you think about where in the crust do we expect mafic and felsic things to be? Well, we expect mafic things, if we think we have, pooling of mantle-derived melts at the base of the crust, differentiating, producing accumulate. We expect mafic stuff down there, but also we expect that to fall off. We expect that to delaminate, whereas we expect if you have, say, relamination, Brad Hacker style, of subduction sediment, you expect that to rise up to the base of the continental crust and stay there. So you expect an input of felsic stuff. And then if we think, well, where do we have mafic rocks in the continental crust? I would argue, actually not a ton in the mid crust because we don't have a lot of large mid-crustal mafic plutons. We might have some under plating in the lower crust, but a lot of basalts come through and erupt at the surface. There's way more basalts than many basalts, few gabbros, many granites, few rhyolites, the classic paper title. So I think we actually expect, an input of mafic rocks at the surface from as basalt, as erupted lavas. And so I kind of conceptually have for a while been expecting that maybe actually the middle crust should be the most felsic, and then really not that much compositional stratification overall. So yeah, I'm certainly on board with a relatively intermediate, not super mafic lower crust. But primarily thanks to delamination, because we should be producing mafic stuff there, just probably doesn't stick around.
All right. Any last questions? Well, if not, maybe we can.
Maybe as people think about last questions, just a couple of announcements that we have a replacement for next week. So we have Leigh Riedman giving talk, I guess, on Mesoproterozoic paleontology, I presume. And then I think Brennan agreed to replace a speaker on December 18th, just before going to Christmas, New Year, sort of talking about second topic of his research. I guess it would be related to great unconformity.
Yeah.
And the last thing I started fill up schedule for next year before summer. So if people have suggestions, feel free to email to any of us.
Thank you.
And thank you, Brennan. And we look forward to see everyone next week.
Thanks so much. Great discussion.
Thank you.